Greetings, Panthers. It's Dr. Augustine. Today we are going to talk about 3 simple gas laws. This video is going to cover chapter 6.3 intro, and there were 3 gas laws that were developed a long time ago, 1700s, called Boyle's Law, Charles's Law, and Avogadro's Law. 2 of these you are pretty familiar with because you've actually probably done the experiment before, Charles's Law and Boyle's Law, although you may not have called it that. Avogadro's Law, I'm going to show you, is a little less obvious, a little more less intuitive, and also kind of more interesting. And so we're going to start right away with explaining these 3 laws, and we will start with Boyle's Law. Now, I found on Scientific American there's a little experiment that you can do yourself if you'd like to try it out. I don't have any pictures, unfortunately, of this experiment, but basically if you take a rather large syringe, you put a small balloon in the syringe, and you put your finger over one of the ends and you pull down on the plunger. What you're doing is effectively lowering the pressure, and what you'll see is the balloon will grow in size. And then as you push the plunger back in, the balloon will shrink in size. Now, probably most of you have not done this experiment before. You probably haven't done a balloon inside of a plunger, inside of a syringe. But here's an experiment you probably have done before. You have probably taken a balloon, my little tie thing on it, and you've probably taken your hands and you've pushed on that balloon. And if you take the balloon and you squeeze it, you are applying external pressure and the volume is getting smaller. So that is Boyle's Law in a very quick summary. So the volume is inversely proportional to the pressure. When we say inversely proportional, what we mean is if the pressure goes up, the volume goes down. If the pressure goes down, the volume goes up. So this one, when we pull the plunger out, the pressure is getting less and the volume is increasing. When we push the plunger in, the volume will decrease as the pressure increases. Likewise, if we take my balloon and we press on it with my hands, I'm going to make the volume smaller. So we say that the volume is inversely proportional to the pressure. If we did this experiment really carefully and plotted out different volumes at different pressures, you would get a curve that would decrease. And if we were to plot P on one axis and 1 over V on the other axis, we would see a straight line. Now, there's a couple little caveats I need to add to this before we go on. And this is only under certain conditions. This is under the special conditions of a constant number of moles of gas. I'm going to use the symbol N for number of moles of gas, and a constant temperature. Okay, so constant number of moles of gas, that just means I'm not adding any gas or taking it away from it. So in this balloon example inside the syringe, we're not adding any gas to the balloon, we're not taking any gas away. So it's a constant number of moles. In the case of my balloon here, I haven't added or taken any away. So that's a constant number of moles. That's a pretty common experimental set of conditions. Constant temperature, as long as we're not heating up this system, then the temperature is going to stay basically the same. Now you might say, hey, wait a minute, your hands are going to warm up this gas. Yes, eventually my hands will warm up the gas, but let's just pretend to a first approximation that my hands are not going to impact the temperature of the gas inside the balloon. If we really wanted to take care of that, we could put some insulating gloves on my hands when I squeezed it, and then it's probably not going to change the temperature very much. But the result is the volume is inversely proportional to the pressure. Sadly, this is a fairly intuitive result. I mean, we've all done this balloon experiment. We may not have done this experiment here, but we've done one where we squeezed a balloon. And we don't get to name it after ourselves because Boyle already made this discovery a long time ago. All right? So, first gas law. It's called Boyle's Law. And the result is the volume is inversely proportional to the pressure only under the special conditions of a constant number of moles, we're not adding or taking away gas, and a constant temperature. Okay? If we have those conditions true, then the volume will always be inversely proportional to the pressure. Let's take a look at the second gas law. This one is called Charles's Law. Now, these gas laws were actually discovered a long time ago. The people who were working on gas phase experiments were actually the military. So these were British and French military groups were developing hot air balloon technology. And the reason they were doing that was not to go out for rides, although it would be really nice to go on a hot air balloon ride. The reason they were doing it was for military advantage. If you could get high above the battlefield, you could see where enemy troops are. So The British and the French were pioneers in this effort, trying to figure out how to get a hot air balloon high up above the battlefield and then, of course, be able to signal down below. If you could see your enemy far away, you could direct the cannons to fire over a certain hill because that's where the enemy was. So this one is called Charles's Law. It is also called Guy-Lussac's Law. Guy-Lussac was a Frenchman. Charles was an Englishman, and they each are sort of credited with this. So this experiment you've also done before, maybe not with liquid nitrogen, but you've done this in other ways. This is also a fairly obvious result. So here's the liquid nitrogen version of this. At room temperature, we have a balloon that's a certain size. We pour liquid nitrogen in, which is very cold, and the volume of the balloon begins to shrink. Okay, the volume gets smaller and smaller and smaller. So in this case, the volume is directly proportional to the temperature. And this is at a special condition of constant number of moles and constant pressure. Okay, so you think about this experiment right here. We haven't added or taken any gas away from the balloon, so it's a constant number of moles, and the pressure hasn't changed. Whatever the pressure is in the room when this was done, that's the pressure, so that hasn't changed. So as the temperature drops, the volume drops, and then correspondingly, if we heated this up, this volume would get bigger and bigger. And so if we were to plot this, volume versus temperature different at a certain pressure, like let's say 1 atmosphere and a certain number of moles of gas, we would get a straight line. That's because the volume is directly proportional to the temperature. Now I said you've done this experiment before. You probably haven't done it with liquid nitrogen, or maybe you haven't done it with liquid nitrogen. What you might have done is you might have left a balloon in your car overnight. And let's say it was a helium balloon. If you left this helium balloon, which is nice floating in your car, and it was a cold night, okay, this doesn't really work that well in the summertime, but if it's a cold evening and you leave it in your car, what happens the next morning when you get there? The whole thing shrinks down and is on the floor. And if you've ever done this and then you brought it in the house, you'd see it would gradually get bigger again and start floating again. Now, if you do this for too many days, it will stop floating because the helium will have diffused out of the balloon. But when you first get the balloon, especially a Mylar balloon, which tend to last quite a while, you're going to discover that if you make it cold, the size will get smaller. You put it in your refrigerator and you'd see this. Another time, which I'm going to challenge you to go see, you maybe haven't seen this before, if you take a water bottle and you drink most of the water out, but you just have a little bit of water left over, you cap the water bottle up, and if you know it's going to be a cold night, stick it inside of your car. And if you come out and look at the car the next morning, like it's got to be cold, around freezing temperatures, you will see the bottle will be all crushed up the next day. And that's because the gas inside of it will have shrunk. After you heat it up again, or once your car's been running and the heater's been on, you'll see it will re-expand, or if you bring it in the house, it will re-expand as well. That's another example of Charles's Law. We're not adding or taking away gas, and it's at a constant pressure. It's the temperature dependence of the volume. Remember, directly proportional means when the temperature goes up, the volume goes up. Temperature goes down, volume goes down. Inversely proportional means when one goes up, the other goes down. One other interesting result from Charles's Law is illustrated in this data here. So again, we have volume plotted on the y-axis, temperature plotted on the x-axis, and what's being shown is 3 different numbers of moles of gas. So these are all at 1 atmosphere, same pressure, and we have 0.25 moles, 0.5 moles, and 1 mole. And if you're able to do this experiment carefully, you start at 0 degrees C, this is the degree C, start at 0 degrees, so like the freezing point of water, and you go up to 100 degrees C, and then you go up to 200 degrees C and 300 degrees C. You could make a bunch of plots on this graph. And then if you drew a straight line between them, you would find that the result is linear, which makes sense. Since they're directly proportional, it should be linear. If you have different numbers of moles, the slopes are going to be different, but they're all going to be straight lines. Here's the interesting part. If you were to extrapolate each of your graphs, and by the way, you could do this with same number of moles but different pressure, you get the same result. If you extrapolated these back all the way back to where they intercept the x-axis, you would find that they intercept at a very specific place. And that very specific place is minus 273.15 degrees C. What that is telling us is there is a temperature below which we cannot go. That temperature is called absolute zero. And that is the coldest temperature we're allowed to achieve. And this experiment actually was the first indication that there was an absolute zero. Now look, we now have tools which allow us to measure things around absolute zero. You can't get to absolute zero, but you can get very, very close to it, nanokelvins away from absolute zero. But back when these experiments were first being done in the 17 and 1800s, there was no possible way to get anywhere close to that temperature. But you could do above 0 degrees C, above freezing point, and at higher, increasingly higher temperatures, and then you could extrapolate those curves, and every single one of them went back to absolute zero. So because there is a 0 point, we can define a new temperature scale. And that new temperature scale, we're going to say, is 0.00. We're going to give that a new unit. We're going to call that kelvins. So 0.00 kelvins is the beginning of the temperature scale, and it goes up from there. So on this figure, we've got degrees C on one axis and Kelvin on the other axis. Technically, it's not called degrees Kelvin. It's just called Kelvin. So if we want to convert our temperature from Kelvin to degrees C, we need to subtract 273.15. And if we want to convert our Celsius temperature to Kelvin, we need to add 273.15. Now, for most calculations, you can get away with just 273, but if you're a precise kind of person and you want to make sure you're doing it really with a high precision, 273.15 is our value. Okay? So we should be able to convert easily between degrees C and Kelvin. We either subtract 273 if we want to find Celsius temperature, or we add 273 if we want to find the Kelvin temperature. One final note on these temperature scales. When you see an equation that has a capital T in it, that's going to imply that the temperature is in Kelvin. If it has a small t, it might be degrees C. It could also be time, but it will depend on the context. But if you see a capital T in an equation, you have to use Kelvin. And the reason you have to use Kelvin is the calculation will not be correct if you don't use Kelvin. All right, we'll come back in a second and look at our third simple gas law.